Okay, I had a question on these, so I'm going to run through a few of the basics real quick. I'm going to start with question 2 here. And the point of this is that there are 4 types of characteristic equations. For 4.2 number 13, for instance, the characteristic equation is r squared plus 2r minus 8 equals 0. The roots of that equation are 2 and -4, which means that the characteristic equation has 2 real roots, and the form of the homogeneous solution is a sub naught e to the 2t plus a sub 1, say, e to the -4t, or more generally, this will be an R1 and this will be an R2. Now, on number 18, for instance, we will have the characteristic equation being r squared minus 6r plus 9 equals 0, which factors into r minus 3 times r minus 3, and the characteristic, or the form of the homogeneous solution is y sub h equals a sub naught e to the 3t plus a sub 1 e to the 3t. But this one needs a t in it. A sub 1 t e to the 3t. So that goes down here with the double root. And also the 3's are just going to be just an r down here. Since they're both the same r, you don't need an r1 and an r2. For section 4.3, number 24, for instance, we're going to have an r squared plus 9 equals 0 for our characteristic equation, and the solutions to this, r squared equals -9, so r equals plus or minus 3i. The solutions are going to be of the form c1 e to the it would be c1 e to the 3it plus c2 e to the -3it, but that can be transformed into another set of constants of k1 cosine 3t plus k2 sine 3t. Note that these have to be in radians. They cannot be in degrees. If you want to convert to degrees, you need to take the 3, divide by pi, and multiply by 180. And that converts from radians to degrees. Should be noted that this is actually c1 times cosine 3it plus I sine 3it, whereas this is c2 times cosine 3t minus I sine 3t, and I should fix this because there should not be an I there or there, which is equal to c1 minus c2i. It is c1 plus c2 times cosine 3t plus c1 minus c2 times I sine 3t. So in any case, if I say q1 equals k1, let's call it, k1 equals c1 plus c2, and k2 is equal to c1 plus c1 minus c2 times I, then we would have a conversion between the c's and the k's that are represented as sine and cosine. In any case, this is the 2 imaginary roots case, so it's going to be, I guess we could use a sub naught still cosine rt, let's call it omega t, and plus a sub 1 sine omega t. So that would be the form in the 2 imaginary roots case. Now what happens in the 2 complex root case? Well, probably just about any of these other problems will have two complex roots. Let's look at problem 21. For this one, the characteristic equation is going to be r squared plus 2r plus 2r plus 2 equals 0. And we'll use r equals negative 2 plus or minus square root of 2 squared minus 4 times 2 all over 2 times 1. This is 4 minus 8 is negative 4 over 2. So it's equal to negative 1 plus or minus 1. In this case, we would have a sub 1 e to the negative t plus it. As a matter of fact, let's write that as a sub 1 e to the power of negative 1 plus it plus a sub naught times e to the negative 1 minus it. But we would prefer to write this with sines and cosines. We're going to write it as e to the negative 1 cosine t plus or minus, or no, just plus a sub naught sine a sub naught e to the, this should be e to the negative t, this should be e to the negative t times sine of t. And I should also point out that these constants, the a1 and a sub naught, are not the same constants as the ones in the cosine and the sine. So that puts the two complex roots, just choosing the constants arbitrarily, but it's going to be a e to the negative t cosine omega t plus a sub naught e to the negative t sine omega t. And I should put the real part in here, a to the negative rt, because that was just a constant down below, but it's going to be the real part and the imaginary part are what's going to go in that and that. Now the point I'm making right here, the author gives the following equation over and over again, where f of t here is called the forcing function. I'm not sure whether the book uses that precise word, but this is basically the part that is pushing the system. Now the forcing functions are going to have some particular form of particular solution. So let me just fill these in. This won't actually take very long at all. If we've got an e to the rt in the forcing function, the particular solution is going to be y sub p equals just a sub 1 e to the rt. That constant, of course, has to be different from the earlier ones. If we've got resonance, that means that your homogeneous solution up here, if the r here in the real roots matches, if either of the r's here matches the r here, then we would need to have y sub p equals a t e to the rt. And if we've got double root resonance, that means we've got this situation down here with a double root. And so we've got the r appearing twice, so that we can't use the t e to the rt. We would have to use a t squared e to the rt. Alright, the others are going to be a little bit simpler. If we've got a forcing function that is a constant, we have a constant for the particular solution. And if actually we could have a particular solution with resonance, because we might have on this one, if we have e to the 0t, if we have 0 as one of the roots to our solution, we should have, if 0 is one of our roots, I think we will have y sub p equals just a times t. And if somehow it's just r plus 0 times r plus 0, I'm not sure what situation that might happen in, but we might have a t squared as our double root resonance. naturally, if our forcing function is t, we won't just have t. We'll have c sub naught plus c sub 1 t. It's a polynomial. And this would be c sub naught t plus c sub naught t squared. And if our characteristic equation is of the form r squared equals 0, then we would have a double zero root, which would be c sub naught t squared plus c sub naught t cubed, I guess. For the t squared, we would need a c sub naught t plus c sub naught t squared, I believe. Well, it goes all the way down from, if we got a t squared here, this is going to go t squared, t, all the way down to the constant. So this is going to go c sub naught plus c sub 1t plus c sub 2t squared. And this one is going to go c sub naught t plus c sub 1t squared plus c sub 2t cubed. And this one would you would just multiply by t again. T to the m, actually you can't really fill this one all the way out because it's going to go t to the m plus, it'll go c sub naught plus c sub 1t plus c sub 2t squared plus dot 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 plus c sub m t to the m, and just multiply by t on each one of those. Cosine omega t is going to be, we're going to have two constants, a sub naught cosine omega t plus b sub naught sine omega t. You don't need those subscripts there really, but it's going to have a cosine omega t term and a sine omega t term. The t e to the rt is going to have some constant a sub naught plus a sub 1t times e to the rt. So it's kind of a combination of the polynomials of this polynomial up above and the e to the rt up above. T cosine omega t is also similar to the polynomial a sub naught plus a sub 1t times cosine omega t plus b sub naught plus b sub 1t sine omega t. And of course, if you had a form with resonance, you would multiply that by t to get a single resonance, and t squared if you had a double root resonance. Actually, I don't think it could happen here. It would never happen with the sine and the cosine because you'll never have a double root with an imaginary root. Finally, on this one, e to the rt cosine omega t, we're going to have basically a e to the rt cosine omega t plus b e to the rt sine omega t. And then if there is a double root, and this was the question I was asking, would it be sufficient to get resonance if we just had omega in our homogeneous solution, or would we both have to have the r and omega? I'm not actually sure of the answer to that question. Intuitively, my sense is that if we've got an omega here, there's going to be some resonance in the system. That is, if the driving frequency matches the resonant frequency here, there would be some I don't know, magnifying vibration. So number 4 is basically just like the answer before. We need to be able to recognize when the homogeneous system is in resonance. That is, when basically when you apply that t to the particular solution. And number 5, be able to set up the linear algebra to find coefficients of the particular solution by using the coefficients in the forcing function. So basically, the particular solution uses the coefficients in the forcing function. That is, well, let's have a look at problem 10 here. This thing has a characteristic equation of r squared plus 3 equals 0. So it's going to have an r of I plus or minus square root of 3i. But we don't really I mean, we can see immediately, let's call this A and B, we could see that this would be the homogeneous solution right here. Y sub h equals this. But we don't really care about that. What we want to do is set our y sub p to be equal to some constant. Let's call it a sub naught. And then we're going to plug in that y sub p prime equals 0, and y sub p double prime equals 1. No, it's not, it's 0. So immediately we can see when we plug that in, we get 0 plus 3 a sub naught equals negative 9, and we can see that a sub naught is equal to negative 3. So our particular solution is negative 3. So let's look at number 17 real quick. It says y double prime minus 2y prime plus y equals 8e to the t. I don't know why I'm writing that again. R squared minus 2r plus 1 equals 0 for the characteristic equation. And we would have r minus 1 times r minus 1. So our roots are r equals 1 comma 1. Okay, so this is a double root of this thing. So ordinarily we would have said our particular solution for this problem was y sub p equals some constant a times e to the t. However, since this is a double root, we're going to have to multiply that by t squared a e to the t. So y sub p is going to be t squared, let's see, a t squared e to the t. Y sub p prime is 2t e to the t plus t squared e to the t, all times a, and y sub p prime is 2e to the t plus 2t e to the t plus, this is going to break out a 2t e to the t plus t squared e to the t. Now we're going to apply that 1, negative 2, 1 to this, so it'll be 1 times this plus minus 2 times this plus 1 times this. Now, everything here is multiplied by a. I like to go crazy with matrices just to make sure I've got everything in the right order. We've got 4 times t e to the t, and we've got 1 t squared e to the t. Down here we've got, let's say, negative 2 times 2 is negative, I'll just write it negative 2 times 2. And here we got negative 2 times t squared is negative 2 times t squared. And this last one is, let's just write that as negative 2 times 1. And this last one is 1 times a t squared. 1 times t squared e to the t. And basically all this is multiplied by a. And all of this is going to be equal to 800 times e to the t. So